Bismillahirrahmanirrahim. Good evening. Today we will start from the previous space lattice. We will introduce the lattice structure, and we will introduce another important information related with this topic. We will learn how much kinds we have in the previous space lattice, and we will try to calculate specifically the right number of volume to the first three kinds to this crystal structure. Let's start from the lattice. Let's know what that's the lattice. What's the appropriate definition to the lattice? The lattice is, we can say, an array of points which are imaginarily kept to represent the position of atoms in the crystal. And we can say it's series. We can say it's array of a series. The both of them are the same meaning. A series of points that are arranged in a distinct pattern. That every lattice point has got the same environment, share the same environment. Hence, one lattice point cannot be. What that's mean? That's mean the lattice point can't distinguished from the other lattice points. Let's go to the next slide. Let's take a look. Now let's know what that the space lattice, or we can say crystal lattice, the both of them have the same meaning. It's a three-dimensional collections of points in space. A crystal lattice structure is similar to a lattice, but here we must note that we must focus on this difference. It's very important. By these few words, we can know the difference between the space lattice and the lattice structure. But instead of points, it's composed of a series of atoms. Here, the difference is a series of atoms, not a series of atoms. A series, sorry, of atoms, not a series of points, like at the lattice. The lattice series or array of points at space lattice or crystal lattice, it's a series of atoms. The environment about any particular points is the same environment everywhere. Here, this figure, this image illustrates to us the two important things. It's the lattice points. Here we have a lattice points in each corner. We have 8 corners in any cubic. That means we have 8 lattice points, not actually 8 lattice points. I will explain that at the next slides. But we have 8 corners. In each corners, we have part of lattice points. And here we have unit cell. We have 6 unit cell in each cubic. Here, we have 7 kinds of crystal system. It shows that only 14 types of space lattice are possible. By that, we have 7 kinds of crystal lattice structure. I will explain all of them. Let me start from the cubic structure, the cubic system structure, and let's know how kinds we have in this kind. What's the cubic system? The cubic crystal system is one of the most common and the simplest class of crystals. Is the simplest one. Okay, here we will focus on cubic system, on these two options, on these two elements. It's are very important. A, B, C are vectors here at cubic system. A, B, C vectors are equal, and all the angles are equal. All of them are 100% perpendicular on each other. Now let's know how much kinds we have in the cubic system. The simple cubic structure, body-centered cubic, and the last one is the face-centered cubic structure. Let's start from the simple one. Let's know what that means, what the difference between this kind and the other, the simple cubic. And the simple cubic structure, there is only one lattice point at each corner of the cubic shaped unit cell. Like I said before, not correctly, we have one atom in each corner, but we will discuss this point at the next slides. Here, A, B, C are equal, and just I have part of atoms in each corner without any extra atoms in the middle or in the face. Now, like polonium, it's a good example to illustrate the simple cubic structure. Now let's calculate the volume, but to calculate the volume, we must calculate another things like atom number, the X to each cubic. Let's start from atom number. We have 8 corners. Each one, in each corner, we have 1 divided on 8, because that we have 1 atom in all this cubic, simple cubic, sure. The fraction of volume occupied by atoms in a body-centered cubic unit cell. It's not important. Let's focus here on the coordination number. What does mean, the coordination number? That's mean how much atoms surround and connected with the specific atom. The specific atom here is the red one. Here at the simple cubic, we have 6 coordinate, that means 6 another atoms connected with this specific atom. Here, let's calculate the volume at the simple cubic. V equal ABC, because ABC, all of these vectors are equal. That's mean V equal A to force 3, like here. Now we will deal with this important form. Vn to simple cubic structure equal n atom, that's mean 1, dot V of spherical atom, that's mean 4 divided on 3 pi to R to force 3, divided on V to cup. V to cup, that's mean equal X to force 3. X here equal the distance from this point to this point equal R. That's mean X here equal to R. Let's calculate all of that. And here we will put pi equal 3.141 instead of 180 to be the result at the last, dot 523 equal approximately 5,200%. Now let's start from body-centered cubic. Corners of the cubic shares an atom, and with 1 atom positioned at the center. That's mean at first the same information about the simple cubic. After that, we put it another. We said we have another atom positioned at the center. That's mean here. What does mean? That's mean here the atom number at BCC will equal to, because 1 at first plus 1 at the middle, to be 2. At atom at the corners of the cup are shared with 8 other unit cells. Coordination number here equal 8. Now, how many atoms in the body centers cubic? The unit cell 9. The unit cell uses 9 atoms, 8 of each are corners atom, forming the structure of the cup, and 1 more in the center of the cup. Like I said before, the corners contribute only 1 net atom, and the center atom contributes another 4, a total of 2 net atoms. Here, this image illustrates to us the shape or the structure to the body structure, BCC. Here we have 1 divided on 8 atom in each corner. We have 8 corner extra. We have another atom positioned at the middle, because that the BCC atom number will equal to ABC. All these factors are equal. Now let's calculate the V at the first, the same thing, but here extra 1 to be atom number equal 2, the coordination number, like I said before, equal 8, IBCC. What that's mean, the coordination number, like I said before, how many atoms are connected with 1 atom or a specific atom. Now let's calculate the D instead of X at the previous slide. Here, something like triangle, 1, 2, the longer one, 3, equal R plus 2R plus R. That's mean D equal 4R. Here, by Pythagorean law, Here we have another triangle, smaller one, smaller than the first one, LXX. From Pythagorean law, L square plus equal x square plus x square. That means L square equal to x square, because that here L square will equal to x square. Now to calculate D square equal x square plus L square. L square, like we know, it's equal to x square. To be D square like that, after that, let's calculate x to be x equal D divided on root 3. When D equal 4R at the previous slide, x will be equal 4 divided on root 3 times R. Now, by use the same form, V will equal 6,800%. That means bigger than at the simple cubic. Now, let's take some examples. Sodium is a good example. Let's illustrate to us the basic cubic structure. Will be like that to sodium. Now, with the last kind of basic structure, with the cubic structure, what is the face-centered cubic structure? FCC is formally defined as a cubic lattice with the face positioned fully equivalent to each of the 8 corners. That means we're dealing with the same information about we have atoms, we have yes, atoms or part of atom in each corner. It was equal 1 divided on 8, but plus position plus atoms positioned at each face of this cubic. Let's go deeply to the information. It's a cup with an atom at each of the corners, but and one at the center of each face. Of each face, like we know, we have 6 faces. That's right. Not actually we dealing with one atom in each face. Why? Because this atom, part of it inside this cubic and shared another part of its body with another cubic, because that we have atom in each face, because every atom share with 2 different cubics. We focus on one cubic because that we will assume we have 3 atoms, because 6 faces dot have atoms. The last equal will be 3, because that the number of the FCC will equal number atom will equal 4. Let me illustrate to you how we could do that. At first, let's take this note. Let's answer this question. How many atoms face-centered cubic? The unit cell uses 14 atoms, 8 of which are corners atoms, like we said before, with the 6 in the center of each of the faces. Since the face atoms are shared by 2 cups, like I said before, they only contribute 3 net atoms to the unit cell. Now let's calculate the volume together. Like I said, equal 4 by Pythagorean law, 4r square equal to x square, and x equal root 8 dot r to be volume equal 7,400%. Let's prove that. Just we calculate x value. Now let's prove V at V FCC equal 7,400% by dealing with the same form. V atom divided on V cup equal atom number. Here it's 4 dot times or dot 4 divided on 3 pi r to force 3 divided on x to force 3. Here we know x equal root 8 times r to be equal dot 74, or we can say approximately 7,400%. Here, let's take some examples. the gold and silver will be good example, illustrate to us the phase cubic structure. This is the gold cubic, silver cubic. Now let's talk about the second kind of structure system, tetragonal. What is the difference between the tetragonal and the cubic system? Let's take a look and introduce all this information. What is the structure of tetragonal? In crystallography, the tetragonal crystal system is one of the 7 crystal systems, like we know before. Tetragonal crystal lattice result from stretching. This is very important, and the difference starts from here. Result from stretching a cubic lattice along one of its lattice vectors. That means one of these 3 vectors will be bigger than or different from the other. Let's take deeply look. Here A equal B vector, but AB didn't equal C. But the angles will be the same. That means the angles here at these 3 angles will keep equal 90 degrees. And alpha equal beta equal gamma. We have 2 kinds, simple and body. The simple, or we can say primitive, tetragonal lattice has 1 lattice point at each corner of the unit cell, like the body, like the simple body cubic structure. Here, the difference is C bigger than, and the other angles are the same. Nickel sulfide is good example to illustrate the situation. Now let's go to illustrate the body-centered tetragonal structure. This is a crystal structure with 8 atoms forming the corners of the tetragonal, like I said before, and 1 atom in the center. Here, at another atom in the center, we have 2 situations. At first, C is bigger than AB, or we can say C bigger than A. Here, C may be smaller than A. The last result is C didn't and don't equal A. We don't have any opportunity to say C equal A here, vector, because that means we will dealing with another situation. What that means we're talking about the body structure cubic. Like indium, this illustrate to us. Indium is a good example to illustrate to us the body tetragonal structure. The last one is, the third one is orthorhombic crystal structure. Let's know what the difference here. Consisting a system of crystallization characterized by 3 unequal axes. What does mean? That means here we have 3 different vectors. A, B, C didn't equal each other, but we still dealing with the same angles. All of them equal 90 degrees. Now we have 4. Actually, orthorhombic is the bigger or huge topic in the crystal structure. This kind has the only kind. I'm talking about the orthorhombic, has the more types from the other. It's the only one has 4 types. The other has 3, have 3 or 1, 2, something like that. Orthorhombic is the bigger kind, or how I can illustrate that. Yes, it has 4 kinds. Is different from the other. Let's take a deep information and introduce all the important information about the orthorhombic crystal structure and what's the difference from the other. Let's start from simple. At first, let me say we have 4 kinds: simple, base, body, phase. Let's start from simple. Let's take a look here. like I said before, we don't have any opportunity to say ABC equal each other. ABC didn't equal each other, but we're still dealing with the same angles. Here, C, B, A, whatever. And like all lattice, it has lattice points at the 8 corners of the unit cell plus an additional point at the center of the cell. Here, like body cubic structure, but with different 3 vectors. Let's take example. The gallium arsenide is a good example to illustrate to us the body orthorhombic structure. Yes, body orthorhombic example. Now, is complete with the face-centered orthorhombic. It's like all lattice has points at 8 corners. Why we have atoms in E and all these 8 corners to build the structure of the shape of the unit cell plus additional points at the centers of each face. Like this image is a good image, can illustrate to us I'm talking about what. Here we have at the six, we have atoms in all of these 6 faces. Now, what we're dealing with the 4th kind of crystal structure is the monoclonic the crystal structure. Monoclonic system, it is one of the structure categories to which crystalline solids can be assigned. Crystals in the system are referred to 3 axes of unequal lengths. Here, what's the difference from the orthorhombic? All of the orthorhombic and the monoclonic dealing with the same different 3 vectors, A, B, C. Let's take a deeply look to know what is the difference between the monoclonic and the orthorhombic. Here, but A is perpendicular to B and C, but B and C are not perpendicular to each other. What does mean? That's mean here between that angle between A and B and A and C will be 90 degrees, but between B and C, because it's not perpendicular, will not equal 90 degrees. What does mean? That's mean alpha equal gamma equal 90 degrees, but doesn't equal beta. We have 2 kinds, the simple monoclonic like sodium sulfide and the base centers monoclonic like ferrous sulfide. Let's talk about the simple monoclonic. Here, this image can illustrate to us the difference. Here, alpha and gamma equal 90 degrees, but gamma that doesn't equal 90 degrees. Why? Because here, like we say, doesn't perpendicular on B or C. The good example to it, it's the sodium sulfide. Now, the base-centered monoclonic structure, crystal structure, base-centered, or we can say shade or end-centered monoclonic lattice. Like all lattice has lattice points at the 8 corners of the unit cell plus additional point at the centers of 2 parallel sides of the unit cell. Here the situation is totally different from the all previous kinds. Let me introduce why. Here what I say with additional points at the centers of 2 parallel sides of the unit cell. That means I will dealing with just 2 centers. Between these 2 centers, we have a condition. This condition is this must be, these 2 centers must be perpendicular on each other. This illustrates, image can illustrate to us the situation. I'm talking about what? Here I have 2 atoms and 2 centers perpendicular on each other. I have extra atoms in these two centers, in these two perpendicular centers. A, B, C didn't equal each other. And like I said, alpha, beta, alpha and gamma equal each other, but alpha, yes, the last one doesn't equal 80 degrees, like I said before, like we seen here, because at C doesn't be perpendicular on B and A. Now, it's interesting situation, because that the monoclinic crystal is very interesting situation. Now, the triclinic crystal structure. It's one of the crystal categories to which crystalline solids can be assigned. Crystals as this system are referred as three axes of unequal lengths that are inclined at. Here, it's too interesting because we're dealing with non-orthogonal and non-perpendicular. That's mean we have definitely different three angles. Let me repeat that. Non-orthogonal, non-perpendicular three angles. Angles relative to each other. Let's take deeply look. The triclinic structure has just one kind. Here we're dealing with just simple triclinic crystal structure. It's also known as the rhomboidal system. It's shaped in 3D like a cup, but it has been inclined to one side, making it up like something like that, not perpendicular, not orthorhombical. All crystal faces are parallel to each other. A rhomboidal crystal has 6 faces, 12 edges, and 8 vertices. Like I said before, A, B, C doesn't equal each other, and here we're dealing with 3 different angles. All of them don't equal 80 degrees anymore at triclinic crystal structure. And we have just one kind of triclinic crystal structure. This is the simple. Here, all these 3 angles are different. We can take an example. This is a good example, illustrate to us the situation. Simple triclinic crystal structure. We can say the copper sulfide is a good example, and potassium dichromate. Now, the 6th one is the trigonal crystal structure. The trigonal crystal system is defined by a 3-fold rotation axis and can be generated from the cubic crystal system by stretching the trigonal difference started from here, by stretching the cup along its diagonal. The symmetry requires the primitive vectors to have the form ABC. Here we come back again. All these vectors are equal, but A, alpha, beta equal gamma, but doesn't equal 90 degrees anymore. But all of them are equal. Just one kind, it's the simple. It shares the same similarity with triclinic. Triclinic has the just one kind, just we have simple triclinic crystal structure. Here the situation is the same. At the trigonal, just we have simple trigonal crystal structure. All these vectors are equal, all these angles are didn't equal each other. Sorry, didn't equal 80 degrees, but equal each other. Like calcium sulfide or sulfide. Like calcium sulfide. Let's talk about the last kind of crystal structure, is the hexagonal crystal structure. This kind is very interesting. In hexagonal crystal system, three equal coplanar axes intersect at an angle of 60. And another axis is perpendicular to the other and of a different length and different angles. Let's take another deeply look here. We have A equal B vector, but they didn't equal C vector. Because like I said before, we have some stretching. Here, let's focus on these three angles. Alpha equal beta equal 90 degrees, but gamma at hexagonal structure equal 120 degrees. It's the bigger angle until here at the hexagonal kind crystal structure. Alpha beta equal 90 degrees, but alpha equal 120 degrees, like this shape. And quartz is a good example to illustrate to us the simple hexagonal crystal structure. This summary, we have simple cubic, three kinds, the base, body, face, tetragonal, and we have some kinds orthorhombic, chromodial, monoclonic, triclonic, and hexagonal. All of them, we have different vectors or equal vectors with equal angles until these three first kinds, simple cubic structure, tetragonal, orthorhombic, all of these three angles are equal at cubic, tetragonal, orthorhombic. But after rhomboidal, here alpha, beta, gamma didn't equal each other. At monoclonic, A, B didn't equal C, and beta doesn't equal 90 degrees. Triclonic, A, B, C, all of these three vectors didn't equal each other, and all these angles are different at triclonic crystal structure. At the last one, hexagonal, A equal B, but didn't equal C. Alpha, beta equal 90 degrees, but the last one, gamma equal 120. This good column to can do great review and focus on these important information. Now, the three common structure is the body cubic structure, face cubic structure, and hexagonal closed packet. All of these three kinds are very important, are very common in our research. Now, let's focus about why we focus on the structure of an atom, what this research gives to us. Insight into the interclass of chemical reaction. When we focus on the chemical reaction, bonds and their physical properties, we can know the electric properties, the magnetic properties, and so on and more than. All of these sources, I depended on all of these. Thank you so much. Have a good time, and thank you about your watching.